In this next section, we'll discuss preparing the data for analysis, which amounts to reviewing the pre-processing steps that are, at least the more common ones that are done before the linear regression. A lot of this is actually fairly historical. In the very olden days, maybe almost none of this was done. With perhaps one of the most initial pre-processing steps being a form of registration, maybe even two-dimensional slice-wise registration. So, back in the day, EPI might have been more commonly acquired as sagittal images because they register well better individually than, say, axial ones. Most of the head motion would stay more in plane in a sagittal acquisition. But now that we do volumetric registration, we can pick a more compact or convenient slice package, which is typically axial. You need fewer slices to cover the brain. So anyway, these steps, in general, none of these are the exact way any of these steps or whether some of them are performed can be discussed ad nauseum. Some of the steps are optional. Some of them are done by almost anyone that does pre-processing, but whether you perform the steps and how you perform them depends on exactly what data you have acquired, the circumstances, and what you plan to do with it once you finish the analysis. For example, if you plan on running a t-test using ETAC for the equitable thresholding and clustering, you might not want to blur the data. But so with those things in mind, let's just review some of the more common possibilities here. This list actually could be much longer, but this is a basic one. So initially, you might run some sort of outlier detection program. By default, AFNI-Proc, if you use AFNI-Proc to run a first level analysis, pre-processing through regression, by default it will run 3D outcount to look for outlier time series, time points in your data. 3D outcount, by default, the basic thing it does is for each voxel, say the voxel here, it finds the median absolute deviation from some trend. So there could be say there's a quadratic drift in the data, it will modestly fit that with some trend, and then it will look for time points that are far away from that trend. So it counts these in terms of median absolute deviation. So what is the it gets for every time point the absolute deviation from that trend, and then how many median deviations are you at each time point. If you're too many, like clearly this spike is, the trend might put you up here, but this is way down here, the program will say that's a spike. So for each voxel, at each point in time, you know whether you are too far away from the trend, and you do call it a spike, an outlier. And that means if you think from a 4D time series point of view, at each time point you can know what fraction of the volume, or even what fraction of the brain masked volume, is an outlier at the current time point. And so now 3D outcount has an option that can tell you the fraction of the mask that is an outlier at each time point, and you'll get a time series for outliers from this. So that's what AFNI-Proc does every time. And you can even generate censoring based on that time series, since any big outliers might indicate motion. Another another program for handling outliers is 3D despike. That is something we more commonly use if the subjects are prone to motion, which is common for some people. If you're scanning kids, for example, they may move a little more. If you're showing the kids stimuli that make them react emotionally or something like that, they may be even more prone to motion. So for cases like that, you might want to run 3D despike or include 3D despike in your AFNI proc analysis. And what that does is instead of just detecting the outliers, it kind of hammers them down a little bit. Still a bigger spike after 3D despike is still a bigger spike. A big spike before 3D despike is still bigger than a smaller one after 3D despike. So it still preserves how far you are from the trend in a relative sense. But it basically, I believe, reduces being more than two median absolute deviations out to an infinite number, say, down to the range of 2 to 4. So it just squeezes them down. So none of the spikes are too huge. And recall that a lot of the operations, even in the pre-processing and certainly in the regression, you care about least squares of differences. And so spikes really kind of mess things up. So there is some good use in running a despike operation. After that step, another step that is sometimes done, sometimes not done, depending on who you ask, is 3D T-shift. That's where you correct for slice timing differences across the volume. So in a common case, as was done with this data, if we add a capital verb to this 3D info option, and I'm going to pipe that through less. How do you spell less? Adding verb makes the capital verb makes the output from 3D info much more verbose. And so it will include all of this stuff plus information for every time point. This just shows the first two. And it will show things like slice timing. So if we hit enter there and hit enter to scroll down a bit, you'll see now it's going through the ranges for each of the time points. But one of the things it shows is the time offsets per slice. And you can see 0, 1 second, little more than 0, a little more than 1 second, a bit more than from 0, a bit more from 1 second, and then up to the very end, almost 1 second, 2 seconds, and then one last slice because it's an odd number of slices in the middle. So basically, over the 2 second TR, it's acquiring 33 slices every 0.06 seconds. And this acquisition order is called Alt plus Z in our AFNI terminology. It's interleaved starting at slice index 0. So the actual acquisition is slice 0, slice 2, slice 4, up to slice, I guess this is slice 30 and 32, and then we come back, that's half a TR, we've gotten the even slices, then after half a TR, now we come back and start collecting the odd indices, slice 1, 3, 5, up to slice 31, slice index 31. And that's at almost 2 seconds. So basically, at the scanner, the 2 seconds are partitioned into 0.06 second intervals where during that time you acquire one slice. But so adjacent slices are basically half a TR apart in acquisition time. In some cases that may make a difference, in some cases not. Basically, if you have if you have like a fast event related design, you may really care about this 1 second, because your fit of the model to the data might be better if you're not off by 1 second from what you're trying to fit to. So in that case, it might be helpful. If you've got very long events, like we have in this with this data, 20-second stimuli, correcting for this slice difference really isn't going to make any difference. But it shouldn't really hurt either, so we do it as the default. And if you don't want it, you just don't include it. Another case where you would not want to do slice timing correction is if the time step were too big. We have a 2-second time series here, but if the TR were large and you couldn't actually capture the hemodynamic, if you couldn't interpolate across the hemodynamic response curve, there'd be really little gain in trying to do any interpolation across the time points. For example, if you've got some stimulus where you play some sounds for the subjects and they have to verbally respond, and so you maybe you'll have a 2-second volume acquisition followed by 4 seconds of time where the subject is allowed to talk, and then another 2-second volume acquisition. Your effective TR for that would be like 8 seconds, 2-second volume plus 6 seconds of subject time. You wouldn't want to interpolate across those time points. So in that case, with a longer TR, you would more likely not do any time shift slice timing correction. Okay, so I'll type Q in my text window where I'm running less, Q to quit the less program, and I'll just drop that window to the bottom and come back to the slides. So after possibly running 3D T-shift for slice timing correction, there can be many registration steps that can be done. In fact, this handout is now a little out of date in that it doesn't account for the way we typically do standard space normalization. But I'll ignore that for now. We'll come to that in other talks. So the basic pieces of registration are: one, you want the EPI data registered to itself. So like here, when you've got the subject's head moving between these two time points, if you're looking at what's going on in the brain here, and at the next time point the subject's head moves, now you're at a different location in the brain, and you don't want this to be changing over time. I'm going to jump back. Let me jump to IJK again. We'll go back to where we were. So you want, of course, the whole time series to be for one location in the brain, across one run or across all the runs you're analyzing at once. So you want to register all the EPI data to an EPI reference volume. And for that we use 3D Volreg to do just 6-parameter affine registration. So the 6 parameters being 3 shifts and 3 rotations. The output, a text output from that is called the motion parameters that give you those six values as a time series. So at each time point, what did it take to register to the base image? And those time series are often used as regressors of no interest, possibly with the first derivatives as well, or first differences. So after that, now that the EPI data is all registered together, you want to get to a standard space. In order to get to standard space, you'll use typically a T1 registration to get to align your subject's T1 to a template T1, but in order for that to be reliable, you really need an extra step of aligning the EPI to the T1. For example, if you acquire the MP Rage or the T1 at the beginning of the scanning session, now the subject's gone through 5 or 10 minutes of scanning, they relax a bit, they cough, you're getting ready for the EPI scanning, and they're now 6 millimeters away from where they were when the anatomical data was acquired. So we go through a step with align EPI and NAT that tries to align the anatomical data with the EPI data. And I won't really cover the details of that here, but it's using the fact that in the EPI data, if we move up farther, you can see, this inner part is white matter, and then you have gray matter around that, and then you have CSF mixed in here as well. The CSF is actually the brightest signal, so here we have the ventricles. The CSF is, in the EPI data, the CSF is the brightest, the gray matter is less bright, and the white matter is less bright still. So that's an inverted color scheme compared with the anatomical data. In the anatomical data, the CSF looks black in here, and the gray matter is gray, and the white matter is white, relatively speaking. That's why that's how the contrasts for the T1 acquisition are based. So white matter is white, or at least it looks like it in the image. So since the contrast values are basically reversed, that's what Align EPI and NAT uses through 3D Alineate to register the data sets. It's fairly strongly driven by the ventricles, by the CSF in the data set. Anyway, so after this point, now we have the EPI aligned to the anatomy and the EPI aligned to itself. And then in the last step, we'll align the anatomy to a template, a standard space template. There are many of them. There are many MNI templates. Typically, you'll pick one based on an atlas that you want to use. So if you have a particular atlas that has brain locations that you want to base your analysis on, you should align to a template that's well aligned to the atlas. And then all your subjects will be aligned to that atlas. So how you do the spatial normalization, in the many years back, we typically used auto-tailor, which is just an affine registration. More recently, we started using auto-warp to do a nonlinear registration, and now we actually use @SSWarper often before running AFNI Proc, which does some iterative method to skull strip and align to the template as one process. And so we might even feed the results of that to AFNI Proc rather than computing it inside. But again, that's for a different session. At this point now, everything is aligned, hopefully. We'll have to review that, but in theory, that's the point of the step. So the EPI is aligned with itself. You know how to align the EPI base volume with the anatomy, and you know how to align the anatomy with standard space. So, for example, within AFNI Proc, it will combine all of these transformations into one so that you don't keep resampling your EPI data. And then now at the end of this, you're in standard space. This could include other registration steps as well, including, blip up, blip down distortion correction, or even additional affine registration across the runs, across the EPI runs. But this is a basic scenario here. So now that basically at this point in time, we've really just done slice timing correction and registration. And now we're in standard space, everything's registered together. Now we just have a couple more steps before we run the regression. So what's common to do after the registration is to blur the data. You can use the default blur is using 3D merge, which is just applying a Gaussian blur of a certain size. The default size in AFNI Proc is 4 millimeters, but you should choose your size based on the voxel size and what other operations you're going to perform. If you're planning on like doing an ICA analysis later on, you probably don't want to blur at all here. If you're planning on using ETAC via 3D T-Test++, you might not want to blur at all here, since you can choose multiple blurring levels with ETAC if you choose to do that. Otherwise, you might want to blur here. There are two basic reasons for blurring the EPI data. One is that the most basic one, I don't know which is more basic, but anyway, one basic one is that when you blur, you do some noise cancellation. If you assume that the noise in the data is somewhat white, then when you average the value of a few neighboring voxels, the noise should cancel a bit, and you should get a somewhat cleaner signal at your central voxel. So you're averaging signal together and hopefully canceling noise. And that does happen. You do get some of that. That's one reason to blur. The other basic one is when you go to standard space and supposing you're going to do a group analysis, the subject anatomical regions will typically not overlap so well. Particularly, back in the older days when we were just using affine registration to some template, possibly even a blurry template, which we don't use so much anymore. You still get a lot of variance in the folding patterns, or even just in how well the sulci and gyri will align across subjects when aligning to your template. So one particular part of the brain, the location of it will still vary a little bit across subjects in standard space. And so if you blur the data a little bit, you make your blobs a little bigger, and then the blobs overlap a little better when you're running your group analysis. Now that we're getting better at registration, we're getting better, EPI to anatomy registration is better, and anatomy registration to a template is better, especially particularly with nonlinear registration. The need to make to account for anatomical variance across subjects drops a bit. So the need to blur is a little lessened because we do better registration. You still need to blur because imagine in one area, one subject has 3 cortical folds and another subject has 2. They can't possibly align perfectly to their template or consistently to the template. And so there's going to still be some spatial variance across subjects. But it will still do a good job. So after you do the blurring step, you might compute a mask. In AFNI Proc, by default, we don't actually apply a mask to the data. If there are some artifacts outside the brain, whether they're motion-based or you're seeing the eyes or ghosting or whatever, we'd like to see the artifacts and make sure they're not something we need to be concerned about. You can actually apply a mask to the data when you do the correction for multiple comparisons, your group analysis. But typically at the first subject level, single subject level, we won't apply a mask. However, we do typically compute masks, and we use them for quality control measures such as temporal signal to noise averaging and things like that. So then the final pre-processing step before running the regression, at least typically, is temporal, some sort of scaling. In AFNI, we typically use 3D TSTAT and 3D Calc to scale each voxel's time series to have a mean of 100. So for each voxel in each run, in fact, we compute the mean, and then we go back, and for each voxel for each voxel at each time point, we multiply by 100 divided by the mean, which is of course constant for that run. But that scales each run by a fixed number such so that the new mean is 100. And at that point, now the data are aligned and they're scaled to, you can call it a percent signal change or a percentage of the mean at this point in time. And now we'll be able to compare things across space and across subjects a little more reliably. And we'll cover more details for pre-processing in the start to finish class. But at this point, we just wanted to review the steps lightly. So now let's discuss the last step here. This is really what we want to get out of this course. We want to understand what it means to run a linear regression and just look at the model and what 3D Deconvolve is doing and what we get as output from it. So the script we're going to run here to solve this y equals x beta plus epsilon equation, that's at each voxel. Y is the time series, again x is the regression matrix. Typically x is constant across all voxels. It doesn't have to be, but typically it is, and it is in this example. And then the output from 3D Deconvolve from the regression is this beta vector per voxel. So for each regressor in the X matrix, what is the beta weight associated? What's the magnitude of effect, you might say, of that regressor? And then air is the residual, epsilon is the residual, what you fail to match from your model to the data. So I'll just briefly look at that RL regress script here. If I do ls to look at the files, we have the script RL regress. And if I cat RL regress, I spell reg, it's exactly what we have in the handouts. So this is a single command. We haven't covered much Unix in this class. I think I'll do a Unix session at some point, but if this is new to you, there are a couple of small details to note about this. One, this is one command, which you could type on the command line, but after making 73 typos and getting all frustrated and quitting before you get it done correctly, it's generally preferable to put your commands into text files, which we call scripts, and then make them look readable. Make them look pretty, line up similar options so that you can look at the command and quickly diagnose what it's trying to do. So we have a couple Unixy characters in here. We have these backslashes at the end of every line, and what they tell the shell is that, I basically you have a command 3D deconvolve and then dash input rl vr plus a ridge, and then the shell sees a backslash. That backslash tells the shell that the command continues on the next line. It's not done yet. This isn't the whole command. And so the shell keeps reading, oh, that's part of the command, now we continue, and etc. So it's as if you typed this whole thing on the command line without all the spaces. That's what the shell sees. Also, parentheses are special characters for the shell. Square brackets are like wildcard characters for the shell. spaces are separators in the shell. So anytime we have these special shell characters in our script, we might want to hide them from the shell because our AFNI command, our AFNI program wants to see them. The AFNI program wants to see, like here, it wants to see 1D colon space 0 space 150. Down here in this basis function for the visual reliable stimulus class, 3D deconvolve wants to see block parenthesis 20 comma 1 in parenthesis. So when we need to hide these special characters, again, parenthesis is this is a special character, the space is special, and this is special. You need to quote these things. And what quoting does is it tells the shell not to interpret them. So the shell doesn't interpret this space, the shell doesn't interpret the parenthesis or the square bracket. Instead, it sends this whole string as it is to 3D deconvolve. So that's why you may see the quotes all over the place in many commands. It's just to hide special characters from the shell and give them to the program in question. In this case, 3D deconvolve. If that's new to you, you'll quickly get used to it. It's not too complicated, but that's all it's doing. It's just hiding things from the shell. So this command we give. This is the full 3 run case that we're doing right now. We're giving all underscore vr plus a ridge to 3D deconvolve. That's the y at each voxel. That's the data it's going to try to match. And let's see what pre-processing has been done to this data set. So here is our all vr plus a ridge. For one, it's 3 runs, so it's not 3 data sets. Typically we use 3 data sets, but in this class we have just 1. And there's a VR there, which suggests possibly volume registration. So some pre-processing has been done. Let's see what. I'm going to run 3D info on this. And this is a fine input. Don't have to have the head. You don't have to have the dot. You don't even really have to have the ridge, but that's good practice. If I run 3D info on that, it shows the history of what was done to get here. And the history shows basically nothing. 3D TCAT was used to put together run 1, run 2, and run 3 from an AFNI proc output directory where this is the result of 3D TCAT. So these data sets are basically original except for removing the pre-steady state time points. So instead of 152 volumes per round, they'll have 150, as we said we want to work with, and therefore 3 runs, you'll notice, have 450 time points. TR is still 2, still 33 slices. Nothing's been done across space. This is just dropping 2 time points and then putting them together into a single data set, which we don't typically do, but it keeps the command small for this class, for the slides. After they were put together, 3D volreg was run with base volume index 2, that's 0, 1, 2, out of this same data set. So ignoring those first 2 pre-steady state time points, this is the 3rd volume, index 0, 1, 2 in this case. So all of the 450 time points were aligned to that volume, and the output is all VR. Sorry for the line wrapping here. I'll just stretch that out a bit so you can see it. There's the command as a single line. And then we asked for the motion parameters to be output. This is the input. Save motion parameters, be chatty. The prefix for the output is RLVR, and we're aligning to time point index number 2. So that's what was done to this data set. which is very little. We haven't scaled it. We haven't blurred it. We haven't done most of the steps in our preprocessing list. So let's just briefly switch to this in the AFNI GUI and just see how that looks compared to what we have here. So I'm going to switch underlay to RL VR, and lo and behold, a couple things we notice. One, our ideal time series is now at the beginning here. It doesn't stretch across everything. That's because our ideal is just for run 1, but now we have 3 runs put together. So that ideal didn't cover runs 2 and 3. But that's okay. We have ideals that will be generated by 3D Deconvolve that do span all 3 runs, so this is okay. So typically when you're going to look at data like this across this, you get many runs here, it's hard to see the fluctuations. Anyway, so that's our input. Our input to 3D Deconvolve is the 3 runs of data, and then again, today we're doing basically a kid's version of the regression where we keep everything simple and fitting nicer on a slide. We're just doing linear trend removal per run. So Polart 1 says for each run we're going to model slow baseline drifts with a polynomial of degree 1. So that includes a constant term, that's the degree 0, and a linear drift, that's the degree 1. Again, for each run we'll do this. So we'll have 3 pairs of regressors for the slow drifts. When we do the grown-up talk later, we'll actually use the natural Polart for the data, which is 3. Natural for how we measure it, at least. The next option is concat, where we tell 3D Deconvolve where the run breaks are. In this case, we input just a single data set. So 3D Deconvolve doesn't know that this is 3 runs of data. It will just assume it's 1. So to tell it there are 3 runs, we'll specify this 1D:0. We'll give the indices where each run start. So we start at index 0 and then 150 time points later and then 150 time points later. Those are the beginning points of each run. And now 3D Deconvolve knows where the run breaks are. For example, it knows to use 3 runs, 3 sets of polynomial drift models, not just 1. Then we give a bunch of stimulus time series as the regressors of interest and other regressors of no interest. We'll give 8 more regressors, 1 for the visual reliable class, 1 for the auditory reliable class, and then 6 more for motion. In the way AFNI Proc does 3D Deconvolve at this point, the 3D Deconvolve command will look a little different, but this is a nice way to view it for now because it more clearly spells out all of the regressors. So the 2 regressors of interest will be based on these 2 options here, stim times 1 and 2. And the format here is we tell 3D Deconvolve when the events occurred, and possibly other things like if there are modulators or durations involved. But in this case, it's just the onsets of our stimuli. And then we tell 3D Deconvolve how to model each one of those events. So, for example, in stim av1 viz.txt, here are 2 stimulus files. If we cat stim av1 tab .txt, we see the onsets for the visual reliable stimulus events. So these are 3 rows of values because we have 3 runs. They don't have to be integers. These are each event onset time is a time in seconds, not TRs, in seconds from the beginning of that respective run. starting at 0. So our first visual reliable event occurred 1 minute into the first run. Our second one at 90 seconds, a minute and a half, 120 seconds. And if you recall, I'll run back for a moment to look at our timing. One event is 20 seconds, and then there's 10 seconds of fixation between them. So event onsets are always separated by 30 seconds. On top of that, there's a mixture of audio reliable and visual reliable events. So in run 1, you can guess that at time 0 and at time 30 we probably had an auditory reliable event. And we can check that if we display AV2 odd dot text. Indeed, there's an auditory reliable at time 0, at time 30. And then the next event must have been visual reliable, visual reliable, visual reliable, auditory, visual, and so on. So that's basically that's the simple format of one of the stimulus timing files. These are just, each row is a set of onset times for that stimulus class, starting at 0. The second aspect of this is, given that you know when the events occur, how should 3D Deconvolve model them? Remember, in this example, each event is a 20-second event where there's a repetition of someone saying simple words and showing you both the visual of that, and you hear the auditory of it. But it lasts for, say, 19 or say 20 seconds. So block 20,1 doesn't tell 3D Deconvolve this is some block design. BLOCK is a particular function in 3D Deconvolve. You can look at 3D Deconvolve -help and pipe it through less if you want to see what. I'll search for BLOCK with a /BLOCK here, or that's a little hard to look for. Instead of doing that, I might run 3D Deconvolve -h web, and that will pull up a web browser, and I could look for the same information. So this takes me to the 3D Deconvolve page, and this might be a little easier to browse. You might be more used to looking through this for information. But I'll just go back to the command line where I can do it more easily myself, and we can see what block is. I guess the parenthesis is special here. So here's block, and it gives you there are a couple block functions. Let me get rid of the highlighting here. There are a couple block functions, but it gives you the basic expression, and you can see what how this is defined.